Hello and welcome to a lesson on probability trees. This lesson is aimed at higher tier GCSE, but it can also be useful if you're doing a statistics module in A-level Maths. To begin then, let's consider the independent events spinning a coin when we can get a head or a tail, or rolling a die where we can get a 1, 2, 3, 4, 5 or 6. Now those are what we call independent events. When one happens, it doesn't affect the probability of the other happening. And we see if we take the two things together, there are 12 possible outcomes. I can have a head with a 1, 2, 3, 4, 5 or 6, and I can have a tail with a 1, 2, 3, 4, 5 or 6. And each of these outcomes is equally likely, so they all have a probability of 1/12, because the sum of the probabilities of all these mutually exclusive events has to add up to 1. So let's have a look at an example. If I look at the probability of getting H3, a head with a 3, and we can either write prob in front of the brackets or just a P to say the probability of getting H3, that would be 1/12. And so would all the others. But what I'd like you to notice is that if we looked at the probability of just getting a head when we spin a coin, that would be a half, a 1 in 2 chance. And if we look at the probability of getting a 3 when we roll a die, that would be 1/6, because there are 6 numbers on the die. But notice that the probability of getting H, a head, multiplied by the probability of getting a 3 is equal to a half times a sixth, and a half times a sixth is a 12th. And we call that the probability of getting a head together with the intersection of getting a 3. That little upside down U means they're both happening. You've got a head and you've got a 3. And that's what we're going to be using in our probability trees. It's called the AND rule. If we want this to happen and this to happen, we multiply the probabilities together. Right, now let's have a look at a couple of spinners, a couple of fair spinners. The first one is a pentagon and it has numbers 1, 2, 3, 4 and 5. The second one is a square and it has numbers 1, 2, 3 and 4. And I'm not interested in the actual numbers, just whether they're odd or even. So let's have a look at the pentagon. What's the probability we would get an odd number? Well, there are 5 numbers and 1, 3 and 5 are odd, so there's 3 chances out of 5. So the probability is written as 3/5. And that means the probability of getting an even number would be 2/5. That's the 2 and the 4. Moving on to the square, the probability of getting an odd here is 2 chances out of 4, the 1 and the 3, and that cancels to a half. And likewise, the probability of getting an even number is a half. And we're going to use that on our first example of a probability tree. So what I've got here is a probability tree that's based on the outcomes when I spin these two spinners. So I've got the pentagon and I'm looking at whether I get odd or even, and I've got the square and I'm looking at whether I get odd or even. And I'm going to use this tree, once I've built it, to answer 2 questions. I'm going to find the probability that both scores are even, and I'm going to find the probability that I get one of each, one odd and one even. To start, I've got to put the probabilities on the tree. So what I've done here is I've just given 2 options for odd or even for the pentagon. And I'm going to write the probabilities on these arms. So what about the probability we said for odd? That was 3 out of 5, so 3/5, which means the probability of getting even was 2/5. Now if we move on to the square, the probability of getting odd was a half and the probability of getting even was also a half. And we write the same down here. Now what's happened here, when I've drawn the first set of arms here for what happens with the pentagon, I've then got to look at each of those in turn and look at what can happen with the square. So there's 2 options with the square. And we've got 4 routes through this probability tree. 1, 2, 3, 4. Those are the only 4 things that can happen. And I'm first going to find the probability that both scores are even. So there's only one way through the tree gives me that. It's even and even. And remember what we said about the AND rule. If you want one thing to happen and another, we multiply in the probabilities. So we get 2/5 multiplied by a half. To multiply two fractions, we could cancel first, or we could just multiply the numerators, multiply the denominators. 2 times 1 is 2 on the top, and 5 times 2 is 10 on the bottom. So the probability of getting even numbers on both spinners is 2/10, or we could write 1/5. Now, what about the probability of getting one odd and one even? Which route through the tree would give me one odd and one even? Well, I could go odd on the pentagon, even on the square, or I could go even on the pentagon, odd on the square. So it's these two routes through the tree that end up here. So I need to work both of those out, and because it's one or the other, that's the OR rule for probability, we add them together. So let's work out the first one. This one is 3/5 multiplied by a half. 3 times 1 is 3, 5 times 2 is 10. This second one, 2/5 multiplied by a half. 2 times 1 is 2, and 5 times 2 is 10. And it's not worth cancelling these fractions in probability because if we need to add things together, we want a common denominator anyway. So this happens, one odd and one even, if that happens or that happens. And we simply add those probabilities together. So it's 3/10 plus 2/10. They're on a common denominator, so it's 3 plus 2 is 5/10. And I could give that in its simplest form as a half. And that completes our first example. Let me just make it clear again that there's never anything else done except multiplying to come down the branches. You always multiply if you want to know what's happened when this has happened and this has happened. Then, if you want one or more of these probabilities here, you always add them together. So it's multiplying down the branches, then adding the various probabilities together if more than one of them are included in what you're trying to find. Moving on to example 2, a more complicated example. A bag contains 4 red balls, 3 blue balls and 2 green balls. A ball is chosen at random and its colour noted. It is then replaced in the bag and a second ball is chosen and its colour noted. Represent this situation with a probability tree and calculate 1. The probability that they're both the same colour, and 2. The probability that at least one green is chosen. Right, well, I've started the tree off. There are 3 options this time for the first pick: red, blue or green. And then for each of those, for the second pick, there are 3 options again. So there are 9 routes through the tree from the root here to the ends of the branches. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Imagine there were 3 picks. We'd then have 27 possibilities. Right, let's put the probabilities on. How many balls are there altogether? 4 red plus 3 blue is 7, plus 2 green is 9. So there are 9 balls in the bag. So the probability of picking a red one when there are 4 is 4 out of 9. So we're looking at a probability of 4/9. There are 3 blues, so the probability is 3/9. Now you may be tempted to cancel that to a third, but I would advise not. Let's keep everything on the same denominator. Next, 2/9 because there are 2 greens. Now we go on to the second pick. Notice that we put the ball back in the bag, so there's still 9 balls in the bag. 4 of them are still red, 3 of them are still blue, and 2 are still green. So the probabilities on these sets of 3 branches will be just the same as they were there. So we'll have 4/9, 3/9, and 2/9. and the same all the way down. And again. So we've got our tree set up. Now we're ready to answer the questions. What is the probability that both balls are the same colour? Well, how many roots of the 9 through the tree give me the same colour? I can have red red, or blue blue, or green green. So there are 3 options. I'll need to work out those 3 probabilities and add them together. Remember what we do coming down the branches? We always multiply. So this is 4/9 multiplied by 4/9. Multiply the numerators and the denominators, that gives 16/81. And now the 2 blues, that's 3/9 multiplied by 3/9, which is 9/81. And finally 2 greens, 2/9 multiplied by 2/9 is equal to 4/81. So the probability they're the same colour is the sum of those 3 fractions. It's 16/81 plus 9/81 plus 4/81. Already on a common denominator of 81, and we've got 16, add 9 is 25, add 4 is 29. So the probability is 29/81. Now we're going to look for the probability that there's at least 1 green in the 2 picks. Well, let me get the rubber and get rid of this working out here, otherwise it'll get in the way. So let's have a look now. I'll have a green pen and we'll work out the probabilities that there's at least 1 green. Well, how can we get at least 1 green? We can get 2 greens, that's included in at least 1, or 1 green. So we could have green green, we could have green in that blue, green in that red, or we could have blue in that green, or we could have red in that green. So there are 5 different ways we can get at least 1 green. So I need to work out those 5 probabilities. This one is 4/9 times 2/9, which is 8/81. Next one's here. This is 3/9 times 2/9, working down the branches. 3 times 2 is 6, so that's 6/81. And now I need to work out all of these 3 because they've all got at least 1 green in here. So it's 2/9 multiplied by 4/9, which is 8/81, and 2/9 multiplied by 3/9, which is 6/81, and finally 2/9 times 2/9, which is 4/81. Well, all these probabilities are in 81sts, so it's just a question of how many 81sts do we have. 4 plus 6 is 10, 10 plus 8 is 18, 18 plus 6 is 24, and 24 plus 8 is 32. So the probability of at least 1 green is 32/81. And that concludes example 2. Example 3. We'll start this one with a clean sheet of paper and draw the tree from scratch. The probability a washing machine breaks down in its first year is 0.1, and the probability a fridge breaks down is 0.2. Show this info on a probability tree and calculate 1, the probability that neither break down, and 2, the probability that exactly 1 breaks down. Probabilities can be given in 3 forms: fractions, decimals, or percentages. We've looked at fractions. Here's an example of probability in decimals. Now I first need to decide what's going to be my first decision point, washing machine or fridge. It doesn't matter, you can pick either. Let's suppose I pick the washing machine. So I need to set up 2 branches from the root to represent the fact that we can have an OK washing machine or one that breaks. And we're told that the probability that it breaks down is 0.1, which means the probability that it's okay is 0.9. And now we'll look at the fridge. So title up here for the fridge, and I've got to have the two options, okay or breaks, and I've got to draw the same thing twice. So the fridge could be okay, or it could break. Okay or breaks. And we're told that the probability the fridge breaks is 0.2, which means the probability the fridge is okay must be the other 0.8. So we want 0.8 on there and 0.2 there. Right, the tree is now complete and ready for use. What's the probability that neither breaks? Well, that means they're both okay. Okay, okay, so it's 0.9 multiplied by 0.8. 9 8s are 72, two figures after decimal points, so it's 0.72 for the probability. Bear in mind, probabilities can never be bigger than 1, so if you get the point in the wrong place, that can be a warning. So the probability neither breaks is equal to 0.72. Now we'll find the probability that exactly one breaks. So how do we get exactly one breaking? It means that the washing machine is okay and the fridge breaks, or the washing machine breaks and the fridge is okay. So it's these middle two probabilities I need to calculate and add together. So this one is 0.9 multiplied by 0.2, which is 0.18. And the second one is 0.1 multiplied by 0.8. Once 8 is 8, but two figures after decimal points in the question, so two figures after decimal point in the answer, 0.08. And I just need to add these two together. This is 0.18 plus 0.08, which comes to 0.26. Remember, we always multiply going down the branches, then if we're collecting probabilities together, we add them. And now for example 4, our final example. In this example, we're going to look at something called conditional probability, where events are not independent, where one event affects another. It's based on the same problem as example 2. We've got a bag with 4 red balls, 3 blue balls and 2 green balls. We're going to choose a ball at random and note its colour, but this time we're not going to replace it in the bag. We're going to put it to one side. A second ball is then chosen and its colour noted. Represent the situation with a probability tree and calculate the probability that they're both the same colour and the probability that at least one is green. And what will happen here is, because we don't put the ball back in the bag, the probabilities down this second set of branches will change. Let's have a look. The first one, we've got 4 red and there are 9 balls in the bag, 4 plus 3 plus 2. So the probability is 4/9. There are 3 blues in the bag, so the probability is 3/9. And 2 greens, so the probability there is 2/9. Now we come to this second set of branches. If we're coming down this route here, we've taken out a red. So there are now only 8 balls left in the bag. There are no longer 4 red because we've just taken one. So the chances of getting a red the second time are 3 out of 8, 3/8. What would be the chances of getting a blue? Well, there are still 3 blue balls, but there are only 8, not 9. So it's 3 out of 8, 3/8. Still 2 green, so that probability is 2 out of 8. Now what if we come this route through the tree? It means we took a blue out, first pick. So there are 8 balls left, but there are still 4 red. So we write 4/8 as the probability. There were 3 blue initially, but we've taken one out. So now there's only 2. So it's 2/8 for the probability of another blue. There are still 2 green, and so there's 2/8 for that probability. This last set of branches, if we take a green out, there are still 4 red out of the 8 balls left, so it's 4/8. There are still 3 blue, so that's 3 out of 8. But there's only 1 green. There were 2 initially, we've taken a green out, so there's only a 1 in 8 chance of getting a green the second time. Now the working for calculating the probabilities now is exactly the same as it was on example 2, but we've got a very different set of probabilities down this column here. So probability that they're the same colour, that means 2 red or 2 blue or 2 green. So we're looking at 4/9 multiplied by 3/8. 4 times 3 is 12 and 9 times 8 is 72. 2 blues, that's 3/9 multiplied by 2/8. 3 2s are 6, 9 8s are 72. And finally 2 greens, 2/9 multiplied by 1/8. 2 times 1 is 2, 9 8s is 72. So everything's in 70 seconds, we just need to check how many we've got all together by adding them. 2 plus 6 is 8, 8 plus 12 is 20. So the probability we get 2 the same colour is 20/70 seconds. We could cancel that down, we could cancel by 4 and say that's 5/18. And now we move on to the second question. Find the probability that at least one is green. And again, I'll rub out what I've got here, so we've got plenty of room to write the new probabilities we're working with. So we now want the probability that we have at least one green. And just as before, there are 5 possibilities. We could have green green, green blue, green red, or blue green, or red green. So I need to work out those 5 probabilities and add them together. So this one here is 4/9 multiplied by 2/8. 4 times 2 is 8 and 9 times 8 is 72. This one here is 3/9 multiplied by 2/8, which is 6/72. And then these 3 down here, 2/9 multiplied by 4/8 is 8/72. 2/9 multiplied by 3/8 is 6/72. And finally 2/9 multiplied by 1/8 is 2/72. So how many 70 seconds have we got? Add them up. 6 and 2 is 8, 8 and 8 is 16, 16 and 6 is 22, 22 and 8 is 30. So the probability is 30/72. And we could cancel that by 6, so we could say 5/12. And that's the probability of getting at least one green. Let's just look back at example 2. Here we've got 5/18 or 5/12, and there we had 32/81 and 29/81. Not the same fractions at all. So at GCSE, usually you have independent events where the probabilities don't affect each other, but you can have conditional probabilities, and you certainly do in A-level questions. Well, that brings to the end this lesson on probability trees. You'll now find an exercise with 4 questions similar to the ones we've just done.